Ocean deposits. Objectives. After attending this lesson, the user should be able to comprehend about the characteristics and types of marine deposits, their origin, classification, and their distribution in different depth zones of the ocean. In addition, the processes that are helpful in forming these deposits will also be understood. Introduction. Ocean deposits are the unconsolidated sediments containing inorganic or organic substances derived from various sources deposited on the oceanic floor. Ocean deposits are occurring as a blanket of sediments on the ocean floors. Their depositional patterns differ from one area to another area. These marine deposits are of two types, as material derived from wear and tear of rocks and deposits of marine animals and plants. Various investigations of the deep sea bottom exhibit a sedimentary rocks consisting of organic and inorganic deposits. The study of oceanic deposits involves the analysis of the sources from which these sediments are derived. Ocean deposits classified. Ocean deposits are broadly classified in two categories as terrigenous deposits that are accumulating on the continental shelf and pelagic deposits that are accumulating on the deep ocean floors. All terrigenous sediments must be transported from land to be deposited in the ocean. Most of the biogenic sediments are produced by organisms which live near the sea surface and must therefore undergo transport to reach the sea floor. Most of the terrigenous particles that arrive at the sea surface are fully destined to become the seafloor sediments. They are very fine-grained deposits. Source and nature of deposits. The marine sediments continuously being deposited on the ocean floor are derived from various sources and are distinguished by the nature of their source regions. Terrigenous material, product of volcanism, organic remains, inorganic precipitation, red clay. Terrigenous sediments. Under the process of disintegration and decomposition, the terrestrial rocks are shattered into pieces. The process of weathering, though not same everywhere, depends upon the character of the rock and climatic conditions. The amount of disintegration will depend upon the time for which the rocks are exposed. These rocks are disintegrated into smaller fragments entirely due to the aqueous denudation. They are also carried down to the sea by rivers as mud and sand. On the basis of texture of the source, region, mode of formation, nature of transporting agency, and chemical composition, the sediments may broadly be divided into three categories as gravel, sand, and mud. The deposition of the terrigenous material varies from coast to coast. For example, the deposits of Atlantic are more terrigenous than those of the other oceans. The deposition of terrigenous materials are mostly assorted. Products of volcanism. Sediments are also deposited due to volcanic processes. There are two types of volcanic material deposited on the ocean floor. One is subaerial group and the other one is submarine deposits. The subaerial type consists of materials that are deposited on the land after being thrown out from a volcano and is subject to chemical and mechanical weathering. Later on, it is transported to the sea by the action of rivers or running water. The lighter materials are carried away by the wind into the sea. After floating for considerable time at the surface, these are deposited in the ocean bottom. Subaerial volcanic materials may also be derived not by eruption but due to the disintegration of basaltic oceanic rocks along the coasts. The process of weathering changes basaltic minerals, lava fragments, andesite, etc., into fine sand or mud in the immediate vicinity on the continental shelf. Organic remains. Apart from the material derived from land, sea deposits consist of calcareous or siliceous remains of organisms. These are particularly derived from the sea, which is the source of life to various organisms. These are categorized into two types as neritic and pelagic deposits. Under the action of the waves, the organic shells and plants undergo mechanical disintegration and chemical transformation, resulting in the formation of mud or sand. They all got deposited at the bottom of the ocean floors. Neritic and pelagic deposits. The neritic deposits consist of dead skeletons of marine animals and plants. The pelagic is a type of algae usually present in the open oceanic environment. These deposits contain only the carbonate of lime, and thus they are different from other deposits on the ocean floor. The neritic deposits are abundant in relatively shallow water of low salinity than in the oceans over great depth, due to the low temperatures of water at depth which is unsuitable for organisms and a small number of plants and animals present there to help in the formation. Inorganic precipitates. Changes in the nature of atmosphere and sea take place as a result of temperature changes or removal of carbon dioxide or greater precipitation. Thus, various inorganic precipitates fall in various parts of the earth far away from their source. These precipitates are never abundant. They include dolomite, amorphous silica, iron, manganese oxide, phosphate and barite, etc. Along with the inorganic precipitates, such products are also found in the sea, which are subject to chemical transformation, namely glauconite, phosphorite, feldspar, phillipsite, and clay minerals. It is very difficult to distinguish between inorganic and organic sediments due to the chemical decomposition. Red clay. It is perhaps the most widely spread pelagic deposit. It consists mainly of hydrated silicate of aluminium and oxide of iron. It was first thought to be produced by disintegration of land. Wyville Thomson thought it to be an organic deposit, that is, a residue of the insoluble calcareous organisms. It could also have formed from chalk brought from the land. But according to Murray, it is a result of chemical decomposition of aluminous silicates and other suboceanic rocks. The nature of the clay is soft, plastic, and greasy. When dried, it becomes a powder of reddish-brown tinge. The red color is given by the presence of oxide of iron. Windblown sediments. The fine-grained sediments that reach the deep sea in regions remote from direct terrigenous sources are mostly wind-blown sediments. These include volcanic ash, terrigenous silts and clays, and some biogenic material such as freshwater diatoms, spores, and pollen. Particles from each of these sources can tell something about the provenance from which they came. The chemical composition and particle size of the volcanic ash tells something of source, intensity, and time of the eruption. Composition of the clay minerals, as well as the types of biogenic material, reflect the climatic conditions of the source region. Biotic constituents may also indicate relative age. Deep-sea sediments in both the North Atlantic and the North Pacific contain substantial proportions of windblown sediments. The clay minerals in both regions are predominantly illites. The rate of accumulation of windblown sediments in the deep sea is typically up to a few millimeters in 1,000 years. Classification of ocean deposits. Murray has classified the sediments according to the areas in which they are found, commonly known as Terrigenous and Pelagic deposits. There is a clear distinction between the Terrigenous and the Pelagic deposits. The former is the result of disintegration of continental rocks brought down by various transporting agencies and deposited on the continental shelf and slopes. The pelagic deposits are mainly formed of skeletons, shells, and some inorganic substances found deep into the sea. Terrigenous deposits occupy a wide range in depth and great variation in color, texture, and composition. The color ranges from blue, yellow to red, and the texture is usually coarser. Coral mud or sand can deposit around such islands by mechanical action. Pelagic deposits are found to be light-colored, reddish or brown, and fine-grained. There is no clear-cut boundary between these two deposits, as the terrigenous deposits may encroach the territory of deep-sea deposits near oceanic islands, volcanoes, ridges and plateaus, etc. Similarly, on the shelf, remains of plants and animals are found in abundance. Wherever these are not covered by terrigenous deposits, they are visible. Thus, both deposits are mingled with one another, yet a demarcation line of 100 fathoms is formed on the basis of predominance of a single type of material. Continental deposits or terrigenous deposits. Here, at least 66% of the deposits are formed of minerals such as quartz. They are further subdivided into the following categories. Littoral deposits. The deposit extends up to 1,000 meters and according to Cunin up to 2,000 meters. The littoral deposits are confined below the high and low tide line. According to Murray and Renard, it is the material which is deposited on the foreshore. They consist of mainly boulders, gravels, sands, and muds. Shallow water deposits. This deposit extends from the shore up to 100 fathoms. The main source of the sediments is in the land nearby. Hence, stone, boulder, gravel and sand are abundant, though mud is also not of rare occurrence. Terrigenous muds. Various types of muds are found beyond 100 fathom line. It contains elements which are responsible for their color. These particles are still finer than that of the sand particles. The neritic deposits consist of the organic shells and skeletons of various animals and plants which are not restricted to any particular sea bottom because of the universality of animal and plant life in the sea. The principal shallow water neritic deposits are shelly gravels and sand found at 50 fathoms depth. The remains are mainly valves of bivalve and univalve shellfish, nullipores, gravel and sand, which are known as calcareous algae, shells of mollusks, spicules of sponge, plates of echinoderms. Their deposition takes place with the help of tidal streams, currents, etc., which carry the eggs in this region. Thus, Neritic deposits vary according to the local peculiarities of the sea, namely the temperature and the salinity of the water, direction of the current, etc. The deep water or oceanic neritic deposits occur around the oceanic islands. The main characteristic is the absence of continental shelf, and only volcanic sand and mud forms the bottom to some extent. Among such types of deposit, coral formation, animal belonging to hydrozoa, is worthy of note. Pelagic deposits. Johnson states that three categories of pelagic deposits are found. Benthos, all rooted, sedentary or semi-sedentary organisms, include corals, sponges, polyzoa, starfishes, sea urchins, etc., and are found attached to sea bottom or sand or mud. Nekton, the marine mammals which can swim freely in waters and have more developed locomotory organs and calcareous skeletons. Plankton, including all unicellular plants, protozoa, diatoms, etc., all smaller crustacean, amphipods, and marine worms. The last one also include various oozes found on the ocean bottoms. Pelagic deposits cover about 75.5% of the sea area. Here, the change from one type of ooze to another is rather gradual and overlapping. Red clay, which is also a pelagic deposit but an essentially inorganic one, is found at the greatest depths. Minerals of terrigenous deposits. Minerals of terrigenous origin can be classified further as metals and nonmetals. The metals of terrigenic origin found in continental margins include placer deposits such as heavy mineral and native metal concentrates, barium in the form of barite and witherite, chromium as chromite, gold, iron as hematite, magnetite and siderite, rare earth elements in the form of monazite and basanite, tin as cassiterite, titanium as ilmenite and rutile, thorium as monazite, tungsten as scheelite and wolframite, and zirconium as zircon. The nonmetals of terrigenic origin are found in continental margins. They include beach deposits such as siliceous sand and gravel as quartz, and placer deposits such as diamond. Classification of deep oceanic deposits. The deep sea deposits comprised of terrigenous sediments also apart from pelagic sediments. Several classifications have been proposed with regards to deep sea sediments. They have been classified into four main classes. Biogenic-pelagic sediments, pelagic detrital sediments, bottom transported detrital sediments, and hydrogenic sediments. Biogenic-pelagic sediments. The word pelagic simply means originating in or derived from sea. These includes oozes and organic compounds. Oozes. Oozes are important marine deposits. Marine organisms secrete a hard structure called tests, which, upon the death of organisms and destruction of organic matter, can sink down to a great depth and deposit as sediments. Deep sea oozes are those accumulated sediments which are made up of 30% or more of tests. Based on the composition, they are further divided into calcareous oozes and siliceous oozes. Calcareous oozes are composed of the tests of foraminifera, pteropods, or coccoliths. Foraminifera are called animals of which genus Globigerina is particularly important, and thus such ooze are generally referred as Globigerina ooze. Pteropods secrete tests of aragonite. Coccoliths are calcium tests of a type of algal microscope plants and are abundant constituent of very fine-grained calcareous ooze. They are very common in mid-Atlantic Ocean. Siliceous ooze. Siliceous ooze is composed of 30% or more siliceous tests derived from number of organisms, of which diatoms and radiolarian are most important. Diatoms are formed of the plant shells, very microscopic in size. The shells are mostly made of silica. It is yellowish or cream colored and turns into fine, white, coherent powder when dried up. Siliceous oozes are found largely in two oceanic zones between 45 to 60 degree in both hemispheres and in limited portions of the equatorial Pacific Ocean. The rate of sedimentation of oozes has been estimated as 11.5 centimeters per 1,000 years. Both calcareous and siliceous oozes contain substantial amount of inorganic clays. Organic compounds. Sometimes the organic matters may not be destroyed completely. Instead, upon their death, they can be incorporated within the sediments, which further reacting with its associated matters can form many organic compounds. Such biogenic-pelagic sediments include peat, coal, petroleum, and related compounds. This type of basin is generally rare. An example of such basin is the Black Sea, which is over 2,200 meters deep and almost completely cut off from the Mediterranean Sea. Here, under stagnant bottom condition, oxygen is depleted and organic matters are deposited. Pelagic detrital sediments include brown clay, glacial marine sediments, and volcanic ash. Brown clay. It is a soft plastic material with greasy feel. It is typically low in calcium carbonate, 30%, and consists of clay mineral such as illite, chlorite, and kaolinite derived from continental sources. Quartz is present in minute grains. There may be minor amount of feldspar and mica. The rate of accumulation of brown clay is extremely slow and has been estimated at 0.1 to 10 millimeters per 1,000 years. Mineral-dominated sediments. Kaolinite-rich sediments indicate warm and humid climatic of low altitudes. Chlorite sediments occur in the Atlantic Oceans in the latitude range 20 degrees west to 20 degrees south. Illite sediments, oceans near the continents. Quartz suggests the presence of tropical desert. Glacial marine sediments and volcanic ash. Terrigenous sediments transported by glaciers and wind are included under this category. Bottom transported detrital sediments. Under this category are included turbidities, contourites, and terrigenous muds associated with bottom currents of oceans such as tides, current, etc. Turbidites. These are important mechanisms of transport of shelf sediments into deep ocean basins where the mass of sediments collapse in the ocean by oceanic currents. The sea water may become turbid water, a process called liquefaction, with a density greater than surrounding water. Because of this density difference, the dense water, turbid water, moves under the influence of force of gravity downward and thus carry along with it muddy as well as bigger sediments along the continental slope and deposit the materials at abyssal floor or trenches. The sediments that accumulated are classified as turbidites. Contourites. Contour currents are those currents in the ocean that operate at deep bottom of the oceans, which are generally produced by the presence of continental slope and headlands. Thus, these currents flow parallel to continental margins. These currents can transport material present on continental slopes and rises towards abyssal floor regions, particularly sediments of the sizes of clay and silt. These currents are capable of winnowing out fine particles associated with coarser turbidites and deposit on abyssal floor with a characteristic feature called ripple marks. Such deposits found by the contour currents are termed as contourites. Hydrogenic sediments. This includes minerals found by alteration or reformed from other minerals in the deep ocean floor. They include Morillonites, Phillipsite, zeolites, and manganese nodules. Some sediments of deep ocean found by alteration of rocks exposed on at the floor of the ocean or by hydration of other minerals. Morillonites is a variety of clay minerals and is normally derived by alteration of rocks exposed on the floor of the ocean or by hydration of other minerals. Chemically, it is hydrated silicate of magnesium, iron, and aluminium. The characteristic physical property of this mineral is that when it is wet, it readily expands. Phillipsites. Phillipsites are minerals which belongs to zeolite group. It is a hydrous aluminosilicate of calcium, sodium, and potassium. It occurs as needle-like crystals. It constitutes as much as 50% or more of the bottom sediments in some parts of the central Pacific Ocean basin, where basaltic volcanic rocks are abundant. Manganese nodules. The occurrence of nodules of hydrous manganese and iron oxides on the floor of the deep oceans have attracted the attention of marine geologists. These nodules are generally referred as manganese nodules. These manganese nodules are objects that often prone to be made up of thick mineral coating surrounding a nuclei. Mineral resources. Marine mineral resources are found either dissolved in the seawater or they can be found as deposits either on the surface or below the surface. Dissolved in a seawater. Each cubic kilometer of seawater contains about 165 million tons of solids, making the 350 million cubic kilometers of seawater the world's largest continuous ore body. 64 of the 92 natural occurring chemical elements are dissolved in the seawater. Sodium and chlorine are the most abundant, accounting for 85% of the sea's dissolved salts. Magnesium and bromium are the other important chemical elements. Minerals of value are gold, silver, zinc, uranium, and thorium. It is also estimated that the ocean as a whole contains about 6 million metric tons of gold deposits. Throughout the world, a ton of seawater contains about 60 milligrams of gold. Only magnesium, bromine, and common salt are abundant enough to be extracted profitably with present prices and technology. Most of the metals such as copper, zinc, gold, and uranium exist in extremely low concentrations. Surface deposits. The surface deposits found on the continental shelf, the continental slope, and in the deep sea zone. The deposits on the continental shelf and slope region are found mixed with sand containing calcium carbonate, iron, tin, uranium, gold, diamond, and platinum. Zircon, monazite, and rutile are found along the west coast of India, coastal Brazil, Australia, New Zealand, Sri Lanka, and the USA. India possesses 90% of the world's monazite reserves in Kerala's placer deposits. Rutile is a beach placer deposit is found along the eastern and western coast of Australia, which supplies 29% of these deposits. Magnetite occurs in these areas where volcanic rock materials are deposited. Such formations are found along the western coastal belts of North America and east coast of Asia in Japan. The reserve of iron-rich sediments in Japan is estimated to be 36 million tons. Cassiterite, which is an important tin ore, is a residual mineral of the weathering of granites. A belt stretches for 3,000 kilometers from northern Thailand and western Malaysia to Indonesia. Here, sediments rich in tin have been dredged for hundreds of years and supply more than 1% of world's market. Gold placers are found to occur along the coast of Alaska, on shelf zone of East Pacific, and in river delta sediments along Oregon, Chile, South Africa, and Australia. Diamonds like gold are found in sediments washed down the rivers in some areas of Africa and Australia. It is found mixed with sand in a belt running thousands of kilometers away from the southwest African coast. Platinum, along with sand, is found in parts of the United States, Australia, and South Africa. Muds bearing copper, zinc, lead, and silver also occur on the continental slopes. Further, they are too deep for exploitation considering the present demand and their market value. Coral sands are mined in Fiji, Hawaii, and along the US Gulf Coast. Sands are mined as a source of calcium carbonate throughout the Bahama Island, which has an estimated reserve of 100 billion metric tons. Phosphorite, which can be mined to produce phosphates needed for fertilizers, is found in shallow waters as phosphorite muds and sands. These muds and sands contain 12% to 18% phosphate. It is also found in the forms of nodules on the continental shelf and slopes. The nodules contain about 30% phosphate, and large deposits are known to exist off Florida, California, Mexico, Peru, Australia, Japan, and northwestern and southern Africa. Sulfur is needed for industrial use. It is known to exist in the Gulf of Mexico and the Mediterranean Sea, where the reserves are to the tune of millions of tons. Manganese nodules and metalliferous sediments. There are two main types of mineral deposits which are economically important. They are the manganese nodules and metalliferous sediments. Both these deposits are related in origin but are usually found in different areas of the ocean floor. Manganese nodules are the most abundant in the deepest part of the oceans other than the trench regions. Manganese nodules are found scattered across the world's deep in the red clay regions of the Northeast Pacific. The nodules were discovered by the Challenger expedition, 1873 to 1876. The last 25 years have been the focus of intense research and development of mining and extraction techniques by large mining corporations and multinational consortia. Manganese nodules are the most valuable deep-sea mineral resource at present. They occur as unconsolidated deposits at the bottom of the ocean. They contain concentrations of valuable metals such as nickel, copper, cobalt, lead, and zinc, all precipitated from seawater. The main sources of the metals probably are marine exhalates as chloride or from the land as hydrated oxides. Metals are leached by hydrothermal circulation along the mid-ocean ridge systems and oxidized in contact with the oxygenated bottom water. Manganese nodules grow radially and exhibit concentric layered structure. The rate of growth of nodules is very slow, being about 0.1 millimeter in 1,000 years. The mineral content of the nodules varies from place to place, shown in Table 1. The nodules contain detrital matter as indicated by aluminium and some organic structures that once lived attached to the surface of the nodule during its accretion. Because the structure of the nodule is rather spongy, their average density is somewhat lower, making them buoyant. These nodules are developed to the greatest extent in the North Pacific, Indian Ocean, and parts of South Pacific Ocean. Metalliferous deposits. These are less well known than manganese nodules, partly because of their potential economic importance has only recently been recognized. Sulfides of zinc, iron, copper, silver, molybdenum, lead, chromium, gold, and platinum have been found along the East Pacific Rise near the Gulf of California. Such deposits are formed by the volcanic discharges of hot solutions containing metal into the sea. Seawater percolates into and through the fractured rocks to form mineral-rich hot solutions due to reactions on mixing. These solutions cool and precipitate, forming metallic sulfide deposits such as those of copper, zinc, and lead. In the Red Sea, deposits of mud of 100 meters thick were found in small basins at depths of 1,900 to 2,200 meters. The evaporation of Red Sea water coming in contact with hot lava has led to salt deposition called salt brines up to 4 kilometers thick. Subsurface deposits. The most important of the subsurface deposits are oil and natural gas. These two deposits represent 90% of the mineral value presently taken from the sea. The major offshore oil fields are found in the Gulf of Mexico, the Persian Gulf, the North Sea, and off the northern coast of Australia, the southern coast of California, and the coast of the Arctic Ocean. There are still many areas of the world that are relatively unexplored in terms of oil and gas. The subsurface deposits are mostly found on the continental shelves where the conditions for the availability of petroleum are conducive. There are many structures which act as a trap for petroleum and natural gas. One such structure is the salt dome, where petroleum and natural gas is trapped in the uplifted and fractured rocks around the dome. In addition to petroleum, salt domes are rich sources of sulfur. Sulfur accumulates around the salt plug because insoluble sulfur containing a compound anhydrite, calcium sulfate CaSO4, is generally present in the original salt deposit. Anhydrite, which is an altered form of gypsum, is insoluble and forms a cap rock mantle over the salt core. With the help of anaerobic bacteria, anhydrite is reduced and hydrogen sulfide gas is liberated. H2S gas later combines with oxygen dissolved in groundwater to yield sulfur. Sulfur is found off the coast of Thailand at 25 meters deep under ocean. Coal is a byproduct of decomposition of thick, lush tropical vegetation and is found on the land surface. But changes in sea level and land geography over geologic time have caused some coal deposit to become submerged. Submerged coal deposits are found in Japan, UK, Africa, and off Mumbai in India. In Japan, undersea coal deposits are reached by shafts that stretch under the sea from the land or descend from artificial islands. Salt domes. Salt domes are largely subsurface geologic structures that consists of a vertical cylinder of salt, including halite and other evaporates. A salt dome consists of a core of salt and an envelope of surrounding strata. In some areas, the core may contain cap rock and sheath in addition to salt. The size of typical salt domes, including cap rock and sheath, varies considerably. In most cases, the diameter is a kilometer or more and may range up to more than 10 kilometers. The typical salt dome is at least 2 kilometers high in the subsurface, and some are known to be higher than 5 kilometers. The cores of salt domes of the North American Gulf Coast consist virtually of pure halite, sodium chloride, with minor amounts of anhydrite, calcium sulfate, and traces of other minerals. Layers of white pure halite are interbedded with layers of black halite and anhydrite. German salt dome cores contain halite, sylvite, and other potash minerals. In Iranian salt domes, halite is mixed with anhydrite and marl, argillaceous limestone, and large blocks of limestone and igneous rock. Salt structures develop in any sedimentary basin in which thick salt deposits were later covered with thick sedimentary strata or tectonically deformed or both. With the exception of the shield areas, salt structures are widespread. By their very nature, the classic salt domes generated by gravitational instability alone are limited to areas that have not been subject to significant tectonic stress. Some salt domes do, however, occur in regions that were subject to tectonic stress. 3 of the many areas of salt structures in the world are representative of all. These are the Gulf of Mexico, region of North America, the North German North Sea of Europe, and the Iraq-Iran-Arabian Peninsula of the Middle East. Economic significance of salt domes. Salt domes make excellent traps for hydrocarbons because surrounding sedimentary strata are domed upward and blocked off. Major accumulations of oil and natural gas are associated with domes in the United States, Mexico, the North Sea, Germany, and Romania, and in the Gulf coastal plain of Texas and Louisiana. Salt domes will be a significant source of hydrocarbons for some years to come. Huge supplies of oil have been found in salt dome areas off the coast of Louisiana. Some individual salt domes in this region are believed to have reserves of more than 5 lakh barrels of oil. Salt domes in northern Germany have produced oil for many years. Exploration for salt dome oil in the North Sea has extended production offshore. Conclusion. The ocean is the final repository of debris from the land. Ocean contains enormous amounts of mineral and sediment deposits. The ocean is the world's largest container of various ore bodies. Phosphorite can be mined to produce phosphate needed for fertilizers industry. Manganese nodules are the most abundant in the deepest part of the oceans. Manganese nodules are most valuable deep-sea mineral resources. The most important of the subsurface deposits are oil and natural gas. Salt domes make excellent trap for hydrocarbons.